Today we are going to discuss the postulates of statistical mechanics. As you have seen that statistical mechanics is broadly divided in two parts. We simply say that the statistical mechanics is of two types. First one is known as classical statistical mechanics, and the second one is called quantum statistical mechanics. So it is obvious that when we talk about the postulates of statistical mechanics, definitely one could think that there will be some postulates on which the classical statistical mechanics have been framed, and there may be some postulates on which our quantum statistical mechanics is based on. Okay, so I have divided this lecture on postulates of statistical mechanics in two parts. In this first lecture on this postulate of statistical mechanics, we are going to discuss the postulates of classical statistical mechanics. Okay, although strictly speaking, systems in nature do not obey classical mechanics. In fact, all the systems of this nature obey the quantum mechanics. They are governed by the quantum mechanical rule, okay, and laws. And in fact, the classical mechanics is just a special limiting case of the quantum mechanics. So logically, we should start with quantum statistical mechanics and then arrive at classical statistical mechanics as a special case. But for convenience and for beginners, we do not follow this actual process, because some of you will not have a concrete knowledge of quantum mechanics, but the classical physics you have studied from very beginning. So I am not following this fact that first of all we should deal with the quantum mechanics, quantum statistical mechanics, and then arrive by taking a special limiting case so that the result becomes the result for the classical statistical mechanics. Actually, we will do this later when we will study the quantum statistical mechanics. Then we will see some of the concept which will be dealt particularly in terms of quantum mechanics, and by taking the proper limit, that result will become the classical result. So this will be done later. Okay. In fact, it is only the pedagogical reasons that we begin with classical statistical mechanics. Okay. And so you can say that from a purely logical point of view, there is no room for an independent postulate of classical statistical mechanics. Okay, it would not be logically satisfactory even if we could show that the postulate of classical statistical mechanics follows from the Hamilton's equation of motion. Even after that, since the world is quantum mechanical, the foundation of statistical mechanics lies not in classical mechanics but in quantum mechanics. Okay. So at present, we take the postulate of classical statistical mechanics to be working hypothesis, just working hypothesis, and their justification lies in the agreement between the results derived from it and the experimental facts. Okay, so this is not very appropriate to say that we are dealing with the postulate of classical statistical mechanics, but as I have told you that for simplicity, for convenience, and for just a pedagogy, we are taking first of all the postulate of classical statistical mechanics, and then in the second part of this lecture we will see in very detail the postulate of quantum statistical mechanics, and after taking the proper limit you will see that those postulates will transform into the postulate of classical statistical mechanics. Okay. Now in the very beginning, in the introductory lecture, when I have started this playlist on statistical mechanics, I have given some introductory facts regarding the statistical mechanics, and you have seen that statistical mechanics is actually concerned with the properties of matter in equilibrium in empirical sense used in thermodynamics. All these things I have explained in my first lecture on this statistical mechanics. You have seen that the aim of statistical mechanics is to derive all the equilibrium properties of a macroscopic molecular system from the laws of molecular dynamics. Okay, and so you can say that the aim of this statistical mechanics is to derive not only the general laws of thermodynamics but also the specific thermodynamic functions of a given system. Okay. Now we will see the important postulates on which our classical statistical mechanics is framed. The theory of classical statistical mechanics is actually framed on which postulates. Now we will learn one by one. Okay. So in first postulate we simply say that the classical system consists of a large number of molecules, or you can say a large number of particles occupying a large volume. So if you consider that n is the number of molecules of a classical system and v is the volume of the classical system, definitely you have to take a very large value of n and v. Typically the magnitudes of these n and v are taken like this. N is almost taken 10 to the power 23, and when you talk about the volume of the system, that will be simply equal to 10 to the power 23 times of volume of a molecule. So if you consider that the volume of a molecule is small v, then the volume of the total system, that is capital V, will be equal to v times 10 to the power 23. Here this v is actually called molecular volume, that is volume of a molecule. Okay. And you can see that these numbers are very large. So in just a limiting case for convenience, it is taken that n tends to infinity and v also tends to infinity. But n and v both tend to infinity in such a manner that n by v is actually a specific volume, or you can say that this is volume of one molecule, because if you consider that volume of a molecule is v and number of molecule is n, then the total volume will be n times v, which is equal to capital V. And so this v will be equal to small v will be equal to what? This small v will be equal to v divided by n. So actually this will be v divided by n, and I have written here actually wrongly. This should be equal to v by n, not n by v. So this should be equal to v by n. This is actually equal to molecular volume. So this n tends to infinity, v also tends to infinity, but in such a manner that v upon n is a constant which represents the volume of a molecule or volume of a particle. Okay. So in nutshell, you can say according to the first postulate, a classical system consists of a large number of particles, and they are actually non-interacting particles, you can say, and large volume. Okay. Now, the second postulate of classical statistical mechanics states that the classical system is always regarded as an isolated system. When you say isolated system, what does it mean? It means this system is not interacted with its surrounding. And when there will be no interaction between the system and its surrounding, there will be no exchange of energy between the system and its surrounding. And if there is no exchange of energy, the total energy of the system will remain conserved, will remain constant. So in second postulate, we simply say that the system is regarded as isolated in the sense that energy is a constant of motion. Okay, this is actually the second postulate. When we will study the Maxwell-Boltzmann distribution law, you will see that we always consider that our classical system is an isolated system, and it does not exchange energy with its surrounding, and so energy is treated like a constant of motion. Now, in third postulate, we what we say in the third postulate, let us see it here. So you can you have definitely studied in the course of classical mechanics. If you have not a concrete knowledge of Hamiltonian and Lagrangian formulation of classical mechanics, I will suggest you go through the videos of my playlist on classical mechanics of my channel. You will get a complete course on the Hamiltonian formulation and Lagrangian formulation of classical mechanics. Actually, this third postulate is related to that. In fact, when you talk about a classical system, the state of that classical system is described in a space which is called phase space or gamma space. Okay. In the beginning of my lecture on statistical mechanics 2, I have discussed the phase space in detail. And you have seen that actually if the number of particles in our system is n, then actually we need 3n canonical coordinates denoted by the symbol q1, q2, so on q3n, and 3n canonical momenta denoted by the symbol p1, p2, so on p3n in phase space to deal with the state of the system. Okay. And so that space is actually called 6n dimensional space or 2f dimensional space, where f is called degree of freedom. Okay. So whenever in classical statistics you want to specify, you want to state the state of a classical system, you must consider that your system is in phase space, and if the system contains n particles, then you will need 3n position coordinates denoted by the symbol q1, q2, so on q3n, and corresponding 3n momentum coordinates denoted by p1, p2, so on p3n. Okay. And if your aim is to deal with the dynamics of that system, what should be the equation of motion? In fact, the Hamilton's canonical equations of motion are used to deal with the dynamics of that classical system. And what are Hamilton's equation of motion? You have learned in the course on classical mechanics, and also I have mentioned these facts in the beginning of my lecture on phase space. So I think you have an idea of this Hamilton canonical equations of motion. This equation of motion is in terms of a function which is called Hamiltonian, and these Hamiltonian are actually this Hamiltonian is actually the function of the generalized coordinates q and the conjugate momenta p. Okay, and what are Hamilton's canonical equation? You can see these are written as qk dot. Actually, qk dot means what? You know, dot symbol represents the time derivative. So qk dot is simply dqk by dt, and actually it represents the generalized velocity. Okay, and according to Hamilton's canonical equation, this qk dot is equal to del h by del pk. Okay, and pk dot is equal to minus del h by del qk. Okay, these are Hamilton's equation. So solving these equations of motion in classical statistical mechanics, we always deal the dynamics of the classical statistical system. Okay. Now we will see what is the fourth postulate of classical statistical mechanics. Okay. In fact, when you are dealing with the problem of classical statistical mechanics, then you consider a macroscopic system, and to deal with this macroscopic system, you only need to know the number of particles n in the system, its volume v, and its energy which lies between E and E plus delta E. Okay. Actually, there may be infinite number of states which will satisfy these conditions. That is, the system has n particles, v volume, and energy lying between E and E plus delta E. Such conditions are satisfied by infinite number of states. Okay. So not a single system is thought, but an infinite number of mental copies of the same system existing in all possible states satisfying the above mentioned conditions are thought. Okay. Actually, these mental copies of the system are actually called an ensemble. Actually, this idea was first of all given by the famous scientist of statistical mechanics, which have played a very great role in the development of statistical mechanics, and he is actually Gibbs. So this ensemble is also known as Gibbsian ensemble. Okay. So this fourth postulate deals with the concept of ensemble. Okay, and I have mentioned it here. You can see the mental picture of. Sorry, the page has been turned, but this will be just okay. Actually, my device gets hanged when I work for a longer time on it, but it is necessary to work for a long time for you. So you can see I have mentioned here that the mental picture of such a collection of system is the Gibbsian ensemble. Okay. In fact, this Gibbsian ensemble is represented by a distribution function, and I have discussed this distribution function earlier in my lecture. Definitely you have an idea. This distribution function is actually called the probability distribution function or the density distribution function, and it is simply the density of phase points or representative points in the phase space or gamma space. And you have seen that this density function is represented by the symbol rho, and in general this is just a function of the generalized coordinate q, generalized momentum p, and time t. Okay. In fact, this density distribution function represents the number of representative points or the number of phase points in unit volume of the phase space. So if you consider a volume element in phase space, you know that the volume element in phase space is what? The volume of element in phase space is simply the product of the volume in position space and volume in momentum space. So we consider that this d3q, this is actually the volume in position space, and d3np, this is volume in the momentum space, and this product d3nq and d3np, this represents the volume element in phase space or gamma space. And as rho is the number of representative point or phase point in unit volume, so the number of representative points contained in this volume element d3 and q times d3 and p will be what? That will be simply rho times this much. So rho times d3 and q times d3 and p, this is equal to number of representative points contained in the volume element d3 and q times d3 and p located at the point qp in gamma space at any time t. Okay, actually this d3 n q, I have denoted this volume element earlier by the symbol dv. Okay, and this d3 n p in my previous lecture I have written it by the symbol d tau. Okay, and the product of this dv and d tau I have written by d gamma. Okay, that is, which is called actually the hypervolume in phase space. Okay, now this fifth postulate is actually a very important postulate of classical statistical mechanics, and in some of the textbook the above four postulates are not mentioned like postulates of classical statistical mechanics, but in some of the standard textbook there is it has been mentioned that there is only one postulate of classical statistical mechanics, and that postulate is related to this principle of equal a priori probability. Okay? So this is the most important postulate of classical statistical mechanics on which the laws of classical statistical mechanics have been framed. Okay, so what is this postulate of equal a priori probability? You can see the name actually signifies its meaning. When you say equal a priori probability, it means there may be different states whose probability will be equal, will be same, and that is known to the observer prior to the event. If the event has not been taken place, but you know what will be the probability of that event, then you say that probability as priori probability. It means prior to the event, the probability of event is in our mind. Okay, actually this postulate of equal a priori probability states that when a macroscopic system is in thermodynamic equilibrium, mark it, when a macroscopic system is in thermodynamic equilibrium, its state is equally likely to be any state satisfying the macroscopic condition of the system. Okay, as you know that a macroscopic system in thermodynamic equilibrium may be found in different states, but all the states will be of equal probability. Okay, if all those states satisfy the conditions of all the macroscopic condition for the state, that is, they contain the same number of particles, same volume, same energy, then the probability of those states of the macroscopic system will be equal. Okay, so in nutshell, you can say that a macroscopic system in thermodynamic equilibrium, uh, when a macroscopic system is in thermodynamic equilibrium, then its state is equally likely to any state satisfying the macroscopic conditions of the system. Okay. Actually, this postulate implies that in thermodynamic equilibrium, the system under consideration is a member of an ensemble which is called microcanonical ensemble. Which is called microcanonical ensemble. Actually, when we will deal with the problem of ensemble, or when we will discuss ensemble theory, you will see that there are three types. There are, although ensemble may be infinite, but we study in importantly three types of ensemble: microcanonical, canonical, and grand canonical. Actually, this postulate of equal a priori probability is just an outcome of the microcanonical ensemble. Okay, and any ensemble which will satisfy this condition which I am just going to mention, that will be called microcanonical ensemble. What is that condition? In fact, any ensemble in case of which the density function or the density distribution function, which you denote by the symbol rho of QP, if this density distribution function is a constant in a hypervolume like this, if you consider that these are two energy surfaces, or you can say the ergodic surfaces, the energy of this surface is E, and that of this surface is E plus delta E. Okay, so if energy lies between E and E plus delta E, then in this region the density distribution function should be constant, and outside of this region this density distribution function should be equal to 0. So any ensemble which will satisfy this condition, that is called microcanonical ensemble. Okay, actually here it is understood that the value of n and v are same for all members of the ensemble. Okay, so this postulate of equal a priori probability implies that in thermodynamic equilibrium the system under consideration is a member of an ensemble, and that ensemble is called microcanonical ensemble. And what is this microcanonical ensemble? If in case of an ensemble the density distribution function rho of QP is satisfies this condition, then you can say that ensemble is a microcanonical ensemble. Okay. Now, the next postulate is actually related to find the average value of an observable in statistical mechanics. As you know, in statistical mechanics, we always talk about the probable value. You cannot measure the exact value of a quantity in one observation, in one measurement. So definitely, when we carried a measurement experiment to measure the value of an observable like momentum, like energy, we get slightly different values. So there is a need to find the average value of any observable. When you say observable, what does it mean? Observable means measurable quantity. For example, you can say that energy is a measurable quantity, momentum is a measurable quantity. So these are called observables. Okay, and definitely we need the average value of an observable in statistical mechanics, because in one step measurement you will never get the exact value of any observable. We always get probable value or statistical value. So definitely we have to find the average value, and how we can find the average value, what are the different types of average in which are found in statistical mechanics, we will see in this postulate. And for this, let us consider that there is an observable in general which I have denoted by the symbol f of qp. This f represents any observable. This may be energy, this may be momentum. Okay. Now, as I have told you that when the system is in equilibrium, then the observed value of this observable f of qp must be a result obtained by averaging f of qp over the microcanonical ensemble in same manner. Okay. If you want to measure the value of f of qp, you have to take the average value. Okay. Now, if the postulate of equal a priori probability is to be useful, then all manners of averaging must yield essentially the same answer. What does it mean? It means if the principle of equal a priori probability holds, then we can say that whatever the method of averaging is used by you, but the result will be same. It means for the same observable, if you find the average value by different methods, that does not matter. If the principle of equal a priori probability will hold, then by different methods of averaging, you will get the same value. Okay. Basically, in classical statistical mechanics, we talk about two types of average. Basically, two types of average. The first one is known as most probable value, and the second one is called ensemble average. Okay. First one is called most probable value, and the second one is called ensemble average. Now we will learn about this most probable value and ensemble average. As the name says, this is the most probable value of an observable. It means, as you know, that if our observable is f of qp, that the value of this f of qp for different systems of the ensemble will have different values. But if you are talking about a large number of systems, then it is possible that so many systems will have same value of f of qp. For example, just as a practical example, let us consider the population of a family. Population of a family. Let us consider there are 4 members in a family. Can you say that age of any 2 members will be exactly same? Definitely not. If there are 4 members, it is least probable that the age of any 2 members will be same. Okay. It means if the number of family member is small, then the probability that 2 members will have same age becomes very small. It is possible that no 2 member will be of same age. Okay. But if instead of a family, you are now considering the total population of India, then what will happen? There may be so many people in India whose age will be exactly same. So in case of a statistical system, since the number of system is very large, so it is possible that so many systems has same value of fqp. And if a large number of system has same value of fqp, that value of fqp will be called most probable. It means the probability of that value of this observable f is most likely or most probable. I think we have understand. Okay, so I have mentioned it here that it is the value of FQP that is possessed by the largest number of system in the ensemble. That is called most probable. So this is a very simple, this will be a very simple calculation. You have to only see the data and observe what is the value of which value of F is of largest number of system. That value will be called most probable value. Okay. Now the second type of average is called ensemble average. Actually this ensemble average is found just by the general technique of finding an average. For this, if you want to find the average value, that is ensemble average value of F of QP, what you will do? You should multiply this observable F of QP by the density distribution function rho. Density distribution function rho. And then integrate this the product of this observable F and the density distribution function Q with respect to the volume element in phase space or gamma space. And after that, you have to divide the integral of this rho with respect to the volume element. Okay, so you can see if this F, I have written it inside a special bracket which represents the average. So if this F is the average value or ensemble average of the observable F, then this will be equal to integral of F of QP times rho of QP D3 and Q D3 and P. Okay, and divided by integral of rho QP D3 and Q D3 and P. Okay, so by this equation you can easily find what will be the ensemble average. Okay, as I have told you earlier that if the postulate of equal a priori probability holds, then when you will find the average value by different methods of the same observable, the results obtained by different methods will not differ much more, but they will be almost same. But it is possible only when the postulate of equal a priori probability holds. Okay, so the ensemble average and the most probable value are equal. What will be the condition under which these two values will be equal? Actually, condition is that if the mean square fluctuation is very small. Fluctuation means what? Fluctuation means what is the difference between the actual value and the observed value. The difference between actual value and observed value is called fluctuation. Okay, and so mathematically we simply say that if the mean value of F square, this first term is what? This is mean or average value of F square minus a square of mean of F. Actually, there is a great difference between these two terms. In first term, we are talking about the average of F square, and in second term, we are talking about the square of average of F. Okay, so in first term, you have first of all you have to find F square and then find the average value of F square. In second term, you have to find the average of F, and after that you have to square it. So when we find the value of average value of F square minus a square of average of F are divided by a square of average of F, if this is much smaller than 1, if this quantity is much smaller than 1, then we simply say that the mean square fluctuation is negligible, mean square fluctuation is very small, And in that very condition, the average obtained either of the two methods will be almost equal, will be same, will be identical. It means in this condition, when this mathematical condition will hold, then you can say that the most probable value and the ensemble average will be same, will be identical. Okay. So when these two average values will be same? The first condition I have mentioned that for this, the principle of equal priori probability must hold, and in another way you can say that when the mean square fluctuation is very small, negligibly small, in that condition these two average values of an observable will be equal. Okay. But think, when this condition will be not satisfied, it means when the mean square fluctuation is not very small, then what will happen? Actually, if this condition is not satisfied, actually there will be no unique way to determine how the observed value of f may be calculated. Okay. In that condition, you cannot calculate the observed value of f. In a simple way, you can say that in this condition, statistical mechanics will not valid. There will be a question mark on the validity of statistical mechanics when this condition which I have mentioned just here, which I am just underlining, that does not hold. In that condition, there is a question mark on the validity of statistical mechanics. In fact, in all physical cases, when we will study this fluctuation in the forthcoming lectures, when we will study the microcanonical ensemble, canonical ensemble, and grand canonical ensemble, then you will see that we will find the fluctuation in number of particle and the fluctuation in energy. You will always see in those calculations that the mean fluctuation, which is actually this much, this mean fluctuation will be of the order of 1 over n whenever you will calculate it. In forthcoming lecture, this will come into in your calculation, that the mean square fluctuation will be of the order of 1 over n, where n is number of particle. And as you know, if this n tends to infinity, in that condition this 1 by n will tend to 0, and so 1 by n will tend to 0, and in that condition the average of f square will be almost equal to a square of the average of f. Okay. And in that condition, you can say that the values obtained by different methods will be same. So I have mentioned it here. You can see in the limit n tends to infinity, the ensemble average and the most probable value become identical. Both will be same. Okay. And now here I have written some facts as a remarkable fact. Actually, these facts I have just mentioned earlier in the beginning of my lecture, that I have told you, although we have studied the some postulates on which our statistical mechanics is based upon, but I have told you earlier that the systems in our nature are not governed by classical physics or classical mechanics, but they obey quantum mechanics. They are governed by the quantum mechanical laws. So definitely this classical mechanics is just a special case, a special limiting case of quantum mechanics. So we should not say the postulates of classical statistical mechanics. Actually, we should study the postulates of quantum statistical mechanics, and then by imposing some proper limit you will see that those postulates will become the postulates of classical statistical mechanics. Okay. So all these things which I have written here, I have already mentioned in the beginning of my lecture. So I am just giving you a reading of it. You have already discussed these things. You can see systems in nature do not obey classical mechanics. They obey quantum mechanics, which contains classical mechanics as a special limiting case. Limiting case. Logically, we should start with quantum statistical mechanics and then arrive at classical statistical mechanics as a special case. Okay. From purely logical point of view, there is no room for an independent postulate of classical statistical mechanics. At present, we take this postulate to be a working hypothesis whose justification lies in the agreement between results derived from it and experimental facts. Okay. So these were a brief discussion on the postulates of particularly classical statistical mechanics, although this is when you say postulates of classical statistical mechanics, that is not very appropriate. So actual situation we will discuss in the forthcoming lecture, when you will find what are the postulates of quantum statistical mechanics on which our statistical mechanics is framed. Okay. So definitely you should watch the forthcoming lecture, which will be on the postulates of quantum statistical mechanics. So I hope you have understand the facts which I have discussed in this lecture, and definitely you have enjoyed. So thank you very much.